Now we will have the last presentation of the day, group 52.
Okay. All right, welcome peers. This is our Capstone group 52. As you can see, our team name here is Ball in. I'm Shamim.
I'm me, Samuel, and Adesh.
And we're missing Joe. But yeah, so our presentation is broken down into 7 components: needs identification, problem definition, design specification, alternative design concept, selection matrix, applicable patent timeline, and applicable patent and timeline. And I'll move on to my groups to present the project.
So needs identification. People in wheelchairs often have trouble doing tasks that require both their hands, or even just one hand at a time, because they're preoccupied in propelling and turning their own wheelchair. So in terms of a few tasks we can think about, it's something like opening a door, or carrying groceries, or really even holding your kid's hand, like let's say if they're a toddler, you don't want them to run away. So we decided to focus on the hands-free mobility aspect of wheelchairs. So we went out and looked for an actual story. So we talked to Adrit Batra, who is a person who is in a wheelchair, and he also enjoys wheelchair sports. And he told us that was one of the biggest problems for him is he constantly fatigued when he was playing wheelchair sports, and found that injury is pretty common. And this is done through the building up the repetition. You're basically doing the same movement over and over again for the propulsion. And also trying to handle a ball while steering and propelling a wheelchair also is a pretty difficult task. So there's a pretty steep learning curve, and it creates a little bit of a reluctance to actually get into wheelchair sports. So we decided to sort of focus on the aspect of hands-free wheelchair sports. Sorry, another thing I should say, the hidden cost. There actually is a lot larger prevalence of injuries, in particular the rotator cuff tear. It's a ligament here that frequently is a problem with wheelchair users, but even more so with wheelchair sports users. Looking at upwards of 76%, so that's like a lot, out of 100 people, I guess 76 is quite a lot. So this is a need statement. Could open up another avenue of enjoyment and reduce the rates of injury for basically any sport where you need to use both your hands. So this would be hockey, any kind of racket sports, even golf if you think about it. So obviously these are not things that you're super focused on doing as a wheelchair user, but if you had something that was hands-free, now you also have a huge avenue of different sports you can access. That might have seemed not applicable. So problem definition, like we said, the wheelchair users are frequently engaged with sports, must use their arms to propel, steer, and handle the ball. The intensity and frequency leads to injuries, and it also constrains the user's agility and natural gameplay, creating a steep learning curve, which creates a reluctance in the sport. So in terms of trying to find requirements, we wanted to first of all focus on the user, so the object interaction and the environment of the design we're making. So we decided to focus in specifically on basketball wheelchair, just because the environment, it's a level field, there's a high coefficient of friction, it's a court, and the objects, so just a basketball and a human user, very easy, very simple to define, and as narrow as we can get in terms of any kind of sports that we can find. Also, wheelchair basketball is a pretty, I think the most popular wheelchair sport right now, or just in general. So first off, we go into vague requirements. So these are non-measurable things, but they are quite important to have on the wheelchair. First off, and most importantly, is obviously the interface shouldn't require the use of hands. Second off is it shouldn't interfere with gameplay when you're trying to control the actual wheelchair. So taking your hands off or the eyes off of the ball, for example, or needing to move in a particular way that affects the gameplay. It should mimic the full range of motion. So typical wheelchairs, you can spin and you can move laterally, but you can't, or you can move back and forth, but you can't move side to side like a normal basketball player could. So having those degrees of freedom in the movement would also open up, I guess, would make it a much more fun activity. The control methods should account for varying levels of disability. So sometimes you'll have people who are disabled from the waist down. Sometimes it could be up from to the diaphragm. So being able to distinguish this and account for it is important. The operation should be simple and intuitive. And lastly, and most importantly, is that it should be really, really safe. Ideally as safe as normal wheelchairs in sports, or even safer. So moving on to more specific numbers. First off is we have the weight, so we're just going to look at the 50th and 90th percentile weights of people, I guess. So second off is the profile. So typical wheelchairs in sports are actually very, very small profiles, so it's easier to actually handle your objects of interaction. So just to be, I guess, kind of scientific with it, we want to be as narrow as the hips, ideally. But if we can't do that, then it would be the arm length minus the diameter of a ball. That would be our biggest profile, as you can see. And we're using anthropometric data for like 50th percentile, something like that. And then in terms of engineering, in terms of speed, so the constraints, we're going to be constrained by what has already been done on robotic wheelchairs. So those numbers, the max speed and the acceleration, has already been done on a robotic wheelchair. So ideally we can reach those numbers. But the objective is to go to the numbers that are done in typical wheelchair sports or basketball wheelchairs. So typically the players in manual wheelchairs will reach these speeds and accelerations. And the angular velocity and stopping distance are implied in the criteria above. Criteria number 4, please ignore that. Instead, we're actually going to be focusing on height. So it should ideally have the same seat height as a normal wheelchair, just because that actually counts for you being able to transfer from one wheelchair to another, from one thing to another. So the height is going to be about 50 centimeters, plus or minus 10 centimeters, to account for any variation in design. And last criterion is the operation time. So 48 minutes is ideal for a full game of basketball, but 12 minutes per quarter, and then you can maybe switch up the batteries. This is because the cost might be too large, or the batteries might be too large. So it's better to have a smaller objective, and 12 minutes is enough for, I guess, a simple game. Like I said, criteria number 4 is actually going to be height, so 50 centimeters plus or minus 10 centimeters.
Okay, so looking at the alternative designs for this problem that we had identified, we have our first design over here, which is the omnidirectional ball drive system, and it's basically a single large ball mechanism that provides 360 movement capabilities through the shifting of body weight. And we like this design because it offers that true omnidirectional movement, and it's also like intuitive control. And but one of its drawbacks would be that it's a complex system, and control is also going to be a bit of an issue when trying to implement this. And the next idea is the Segway style balancing platform. It's a 2-wheel platform. It uses a gyroscopic stabilization to lean, and it utilize lean to steer control. And this is good too because it's already a proven responsive control like technology and good stability, but it's limited to back and forth movement, and also to balance requires continuous power. So those are the drawbacks. And third design, we have this metronome wheel system, which is 4 wheels that are rollers at 45-degree angle, and that allows for the omnidirectional movement. So it's precise control, and it distributes the load pretty well. But obviously it's very complex wheel design, and the maintenance would be very intensive. So moving on to the 4th one, we have this track-based, which is just a continuous track system with a central pivot rotation, kind of like a tank. And it's good because it offers good traction, and it's simple control logic for control.